I'm Mark Hahn. I work for a consulting company. I'm their director of DevOps. So my role is everything around software velocity. We work with small, medium-sized, and large corporations to help them gain efficiencies out of their IT operations and to innovate where they can. So we'll talk about one of those ways that we innovate. Let me ask here, I assume people here use software and try to deliver software. So if your organization delivers software at least once per quarter, raise your hand. That should be just about everybody here. Everybody's dealing with software. Okay, everybody raise your hand. Up high, come on, so we can see it. Okay, keep your hand up if you can do that once a month. Okay, good. How about multiple times a month? Okay, fewer hands. Can you do it weekly? Multiple times per week, daily? Okay, a couple of people, multiple times a day? Yep, good. So there's a spectrum here, right? And part of what I do is to help people, deliver software more efficiently. But a lot of the companies that we deal with are struggling to get here because they have processes that are built to essentially slow down software delivery. We'll talk about container technology and how that really helps, and there are a lot of different facets in the way that containers can help you. So we'll talk a little bit about why to use containers, and then we'll talk about how you can start using containers very easily, just getting started, and then use them throughout. So, this is from the Cloud Native Computing Foundation, and of course, this timeline is scaled to their timeline. They think the world started in 2000 when Sun started building container and virtualized operating systems on top of Sun OS. In reality, and those virtualized systems led Amazon to build infrastructure as a service, right? They were doing this internally and they figured out they could sell it. And then we went into open source kinds of infrastructure as service and platform as a service, and then finally using containers and delivering containers as a way to get to a cloud native environment where you had a lot of flexibility around how you delivered software. You don't become cloud native overnight, so we're not going to try and do that. But this virtual memory and the containers that support isolation of small units of computing has been around since for 50 years, since the 60s, and IBM's been doing it. If you go to the Wikipedia page on VM, it will talk about IBM's early days of doing this, right? So we've had 50 years of expertise in dealing with this in old school legacy systems. So we can take advantage of that knowledge and reapply it. And so there's a bit of management speak here. Why does that history matter to you? It's because we do have the engineering expertise to do this stuff. It's manageable. It's not as hard. It doesn't have to be cloud native. It doesn't have to be all Netflix and Google. You can use this at a much smaller scale, a much more human scale, and adapt it to your enterprise. And we've got lots of experience that lets us do that. If you're in an IT organization, there are 3 triangles that you are using to juggle what you're doing. The first triangle is time, cost, and quality, right? So you've got to juggle those things. How fast can you get software out? Can you release it with enough quality? And what does it cost you to do that? Can you do it efficiently? And then information security, which I've been very important in my career. Started on Wall Street banks. Information security was very important. It's now, headlines in everyday newspapers, right? And there are 3 things in security that you've got to cover. Confidentiality, can you make sure that the data is kept secure, that needs to be kept secure? Integrity, can you make sure no one's changing that data? And then availability, can you make sure you can get at the data when you want to? So the question is, how do you get to all 6 of those? How do you satisfy all of those at the same time? That's a lot to juggle. Well, it turns out that containers and container orchestration, Kubernetes and Mesos and so forth, allow you to do that. And I'll talk to you about that. So I want to talk a little bit about the whys. I'm going to address each one of the points of those triangles here as to why you want to go into containers. Number 1 is time, or rather cost. Containers allow you to make better use, better utilization of the hardware and the computing systems that you've already got. So when people started spending money on these large computers, they wanted to make sure that they were using them, morning, noon, and night. And that's that was very important, but cost of computers drove down. We had the PC, and it didn't matter. You could turn it on, use it for 2 hours a day, and it was still cheap enough you didn't care. But when you're at scale, it does matter. And most computing shops, if you run a data center, if you have an organization, most people are using about 10% of their capacity. They're wasting 90% of it. Just because, at scale, we don't manage stuff that way. We buy multiple systems, dev, test, UAT systems, and they sit unused most of the time. And so effectively, while your production systems may be running at a higher utilization, typically around 30 or 40%, all of those other systems are way underutilized. And the net effect is overall they're costing you a lot of money for a bunch of capacity you don't use. This sort of depicts that grade. So, if you have one big machine and you put one big application on it, you can only fit one of those big applications on it. If you do some sort of shared web hosting or something, now you can get multiple units on here, and this thing is packed 33% more efficient than this one by measured volume. And if you get to containers and microservices, you can get to essentially use almost the whole container, nearly 100%. And that's about 50% more efficient than this thing. And that's the secret that Google uses. By doing virtualization in containers, they're able to get a lot more utilization out of the systems that they've already got in-house. So the other is quality. Containers allow you to take the pieces of your applications, the software that you run, and put them into isolated units, and you can measure the quality of those units. So you're allowed to, you can put them essentially in a test rig and test how well they work. And the other things that change that cause that software to work or not work, they're limited by the infrastructure that the container describes. So you can better test the quality of these things. You can better describe the environments they run in and limit those environments to the ones that work. Time. Containers are just easier to work with. They take a lot of your infrastructure that is now much of manual process and allow you to make that an automated process. So you're describing in automation or in code how that application is expected to run, the hardware that it runs on. That gives you a great leg up over what you were doing before. Instead of having Visio diagrams that showed a whole bunch of network pieces and size of systems and so forth, we now just get that information in a file that we can check into code, and I'll show you some examples of this in a minute, that you can check into code. The network interfaces are in there, so it becomes self-describing, and that saves you a lot of time in getting this stuff done. The other thing is it allows you to deploy faster, and so this is sort of a graph of what it costs you to deploy software. If it takes you, say, several weeks to get a deployment out the door, this is the cost that you've spent on building that software that you're getting no business value out of. So that the analogy is, this is inventory that you've built that you can't sell. So it's inventory, it's widgets that you've built up and are sitting in your warehouse or are sitting at the end of your assembly line, but you can't make effective use of those. They're not effective until you get them released and into store shelves where you can sell them. At that point, they become valuable. This is all of your software in the test phase and UAT phase is unsold inventory. It's costing you money. You've spent the money to build this software, but you're getting no business value out of it. If you can release much smaller increments, you can realize that business value sooner. If you can build a doll or a widget quicker and get it into the store and sell it, now you don't have to finance that widget anymore. You don't have to finance those parts for it. So it turns out that if you can do that, the cost of this is about, say, call this 10 units. This is only like 1.2 units. So you're saving nearly 8x the effort and the costs. And this is actually real money that your CFO sees, certainly at scale. Availability. So containers can be restarted very, very quickly, and they allow you to measure. They build an interface that allows you to measure that your application is up and running and doing what you expect it to do, and if it stops, you can restart them. So in terms of availability, containers allow us to make our software much more available. And there are orchestration tools and the rest around the ecosystem, but even starting with just containers without any of the rest of the ecosystem makes your life easier. Integrity. So a container is actually built on security features inside of the Linux operating system and also in Windows, C groups in Linux, that isolate a process from other processes, and so they allow you to enforce a lot more integrity constraints on your running application software. This is a huge boon, both for your security company and also to eliminate your security organization and to eliminate bugs as well in your software. So it does a great job of doing that. Finally, confidentiality. In the same way that the container can't break across its barriers and screw up things on the outside of it, they limit what can come into the container through the storage interface and the network interface. So they also help maintain the confidentiality of the data that's in there. And those controls that you get out of using containers gives you a leg up on each one of these processes and help you get more efficient. So I've convinced you that containers are important. They're going to save you money. They're going to make your software more secure, cost less, taste great, and all that. How do I actually use this? Well, we're going to take our first steps into infrastructure as code, and it turns out that you can take your legacy applications as they exist and not really change them, put them onto containers, and now you get much bigger control of that. Very easy steps here and I know that this sounds pretty, it can't just be 4 easy steps, but it is a fairly small process to have to deal with. So you can put container software onto your existing systems. Putting Docker Enterprise on an existing set of hardware at the development layer or on your test machines does not interrupt what's already going on. It's relatively lightweight when it's not in use. And then when you start deploying to the Docker container, you're going to be moving workloads from your traditional, you're going to shut down your old app and install it as a containerized version on that same hardware, and the overhead of running that is small. So you can actually run this side by side on your existing hardware. You can experiment in your dev test and prove to yourself that yeah, we can deal with this stuff. Installing Docker Enterprise doesn't crater my existing infrastructure. Then you work on creating the containers, the actual, moving your software into a containerized environment. There's some work that has to happen there, but it's relatively straightforward, and it doesn't have to slow down the development that you're already working on. It's building the right specification file, testing that specification file, and sort of rinse and repeat. And when that's ready, now you can begin to deploy it. So you can use the tool set that comes in Docker Enterprise to deploy that. It's more automated than your manual deployment because you've had to specify stuff. So now you're open to automation. This helps, saves you time, and the automation also increases repeatability, meaning you're more accurate, you have higher quality deployments. And then you take what you've created here in terms of specifications in those automated deployments, and you check those into your source code control system. Now what you've got is the processes that you use to release code. It's now version controlled. If you change your code or you need to change that release process, you can go back and look at prior versions of how you release this. This is huge from an audit perspective. It's also huge from a repeatability perspective. Safety, just being able to deliver better. It also, if your application changes, you've got a record of what it looked like before in terms of what network interfaces it used to use and what ones it uses now. That's all built into your infrastructure code. So again, from an auditability perspective, from an operations perspective and so forth, this is a big leg up. So let's just basics of the Docker process that are here. I'm going to show you examples of each one of these phases. So in there are 3 steps to Docker. You compose, you push, and you pull. So Compose is about building the Docker container. So you're going to take a specification for this container. That specification is going to identify the application that you want to run and anything else that's needed in that virtualized environment to run. After you build that, you can do some bench testing, and then when you're satisfied that that is the container, or you can then store that in a registry. So you're going to store a copy of that in a secure location, and that then allows you to go back and look at prior versions of the software that you've released. But that's called the registry. And at this point, what you've got is an image. So you don't have anything running yet. You've got it's called a Docker image. And then at the pull stage, when the application is ready to run, you pull that image onto a particular system and you run that container. So now you're actually running the container. So up to prior to running, you've got an image, and then when it's actually in operation, it's a container. So the way that Docker works in particular, and there are multiple runtimes that you can use for this, RKT and a couple of other projects that are in the Cloud Native Computing Foundation. They have different trade-offs of things they want to do. Some of them, RKT in particular, is a little bit faster than Docker is, and it's a little bit lighter weight. So it's got some valuable features. So Docker owns the mind share of containers, but you've actually got a choice in the containerized environment in terms of what you can run. But with Docker, you start with essentially a base image. Here's an operating system or an operating environment that I want, and it's got to have a particular version of my OS, my Linux version of OS. It's got to have a particular version of the runtime that I care about, say the JVM, the Java Virtual Machine, or possibly of .NET, if that's your code, or whatever, your Python libraries, your whatever. That's the base image. And you can find if you're dealing with public and open source stuff, or just leveraging open source into your private world, there are hundreds of thousands of base images available on Docker Hub. So whatever flavor of technology that you're working with, whether it's PHP or Python, Java, et cetera, whatever is your flavor, you'll find a base image that gets you really close to where you want to be. Then you add your application-specific stuff to it, the WAR file or the particular executables that are the result of your C# compilation, or your Python environment, your Django environment, whatever happens to be there. You build that image, and what it does is it's very similar to starting up that machine and then hibernating it. So you end up with a specification of something that's already started to the point that it can be restarted from that point. So very different than rebooting. It's more like returning back from hibernation. That's where we get a lot of the startup speed out of containers. This is a Dockerfile, if you haven't seen one before. It's a simple application, but also a very simple file that goes with it. So we start with it's a Spring Boot app. So in this case, all I need to do is start with the Java JDK. I create a location, and it is effectively at this point, when I say start with this image, it is a complete Linux image. I think on Ubuntu, if I'm not mistaken, but I can use other operating systems if I want to use CentOS or whatever my operating system du jour is. I start with a VM that's built out that way, that a VM virtualized environment that looks like Linux with Java installed on it so I can run Java programs. I create a directory in the root for my particular application that we call Workspace. This is sort of a common idiom. And then I add in, all I need to add to this, because I've got the Java runtime environment, all I need to do is add my jar file, which runs on its own. So because I'm using Spring Boot, I've got a web server built in. If I wanted to do this with, say, a Tomcat environment or a WebSphere environment, I could start with that WebSphere environment and add just a web application file to it. If I wanted to start with IIS, I could do that and then add in my C# MVC code onto this image. I set up the networking ports that I'm going to expose. In this case, I'm using 8080. That's common. I could also use port 80. I could use other ports if I wanted to. But at this point, what I've done here is that I've said the only access into this container is through the web port. And that means that you can't SSH into the box. You can't go see if there's an Oracle database on this box. You can't go. Everything else is contained. Every other network request across every other port will return an invalid error to that device. So now I've greatly reduced the attack surface area to this thing and increased the security and stability of this application. I can also do the outbound side. I could limit the number of ports that this thing could access going outbound and set those up as needed. And then this command says, when you start this container, what happens? And this is what happens is we run a jar. So this thing is an executable jar, and it runs a web server. And so when this container gets started, a web server fires up that's listening onto that port. And that's the magic. This is very simple. It's a very easy thing for developers to jump into. So next thing you do after you've built that, the image is sitting locally on your system, but you want that available throughout your enterprise. So you're going to push to a registry, which is a common storage area, which is where all of your Docker images get stored. You can use a public one if that's what you want to do. Probably not likely if it's your own source code, so you can build private directories. You can use open source software like Artifactory or GitLab to house your registries. This is fairly easy to accomplish in your organization. And then it's a database of all of the runnable images that you've got. But this makes it very easy to know your current version and all your prior versions and your test versions, and with a little bit of naming scheme. Like this makes it very easy to know what software you're running, what software you plan to run, and what you've run in the past. And then with Docker Run, fundamentally it retrieves an image out of the repository you tell it and runs that image, and it takes just a few seconds to start up. So this is a lot easier than what you've done is you've pre-configured all that server specification, so you don't actually have to build a server to go run this thing. So, for example, if you've got your main development branch for your particular application, and now you want to do something different because you want to do a demo for some client whose business you want to win, but you don't want to mess up what you're regularly doing, you can very quickly build a separate machine that's got all the specifications needed for that demo environment that you want for that customer, and not interfere with anything else, because it's limited. And if you go back later, you've got a complete record of that thing, and if you're smart, you'll have checked in that code. So if that customer says, yeah, I'm not interested, but then they come back in 3 months and they go, that really was a great idea, I'd love that, all that stuff's checked into your code. So those are the sorts of things that happen in the real world. People are fickle and change their mind. They like a feature, they don't like a feature. We've got a record of that stuff, so when they do decide they really want that, you can go back and find it. And while testing it, it hasn't interfered with your regular process. So assuming that you're going to get more mature with this, and rather than just running a single Docker container, you're going to go to Kubernetes. And I'm not going to spend a lot of time with Kubernetes, but basically Kubernetes is the engine that allows you to run lots of Docker images in ways that limit, that reduce your overhead for those operations. Kubernetes is a pretty complex beast, but from an application development problem, you only care about a very small piece of what everybody's going to tell you about Kubernetes. If you're an application developer, you care about the fact that it runs your Docker containers according to your specifications, and you just say, I want to run X copies of this thing, just go run it, and Kubernetes makes that happen. So if you buy a Kubernetes book to try and learn about it, and what you really care about is delivering software, pretty much you can skim over the first 23 chapters and get to chapter 24 and 25 at the end of the book, where they start describing about how developers use this software. The rest of this stuff is really interesting, but I can go to GCP, Google Cloud Platform, and say, I want a Kubernetes cluster, and in 2 minutes, I've got a complete cluster that will then start running my applications in seconds and scale it up and scale it down. And to me, that's like very, very fast. I don't have to deal with asking permissions. I don't have to build a release plan. I can just go test software. And then when that software is right and solves the right business problem and looks good, then it's really ask for forgiveness that I didn't follow the right rules, because now we're going to make money off this software. So this is what a deployment looks like in YAML in all of its glory. There are, if you want to look at it, it basically says I'm a deployment. I want to run on Nginx. I want to run this container, and I want you to run 2 replicas, and that's all I care about. And so while there's a little bit of syntax in here, oh, and by the way, it runs on port 80. This is a container specification that's different than the Docker specification I gave you before. But what this allows me to do, 2 things. One, it's code, but it's relatively simple and readable code, so developers can grok this stuff and know what's going on. And number 2, it's code, so it's stored in your code repository. So again, it's version controlled, it's auditable, it's recoverable. All the things that are useful in a real world environment. So this is why Kubernetes, yes, it's a complex beast, but when you're at that level, it's the complexity you need, and you'll understand how to deal with it when you need to get there. For legacy environments, if you're going to just deploy an app on Docker, you can do that and then be prepared for this level without actually having to go to Kubernetes for all that stuff. So Kubernetes, or containers in themselves, in the container ecosystem, you can start out with just very simple, straightforward containers for your legacy application that you really don't have to change. It doesn't matter that you've got a monolithic application. I have customers that are deploying 30 and 40 gigabyte applications in memory footprint onto their container environment, onto their Kubernetes, and are running just fine. And these legacy applications are a lot more stable in that environment than they were prior. And that's the value that you get. It allows you to take that first step towards doing lean, agile DevOps, where developers have end-to-end responsibility and you have a product-driven focus. So, I mean, from my DevOps world, I think of this as essentially the continuous process that we run, and we want our developers to be involved in all phases of this. So first of all, we take a product-driven approach, which means that the developers are equal partners in creating the product that gets delivered. They help plan what makes sense, and they're gonna sit in the discussions and brainstorm and compromise with the product planners, with the business people that care about the software. They can build it, get continuous integration. They can build automated testing using containers as a framework to limit, to be able to bench test each piece of software and then test the interactions between them. Automated deployment, automated monitoring and various monitoring. So you're not only watching just like, is the app up? Is it not consuming too much CPU? But how many features are being used? Are they being used in the order that we expect them? What are the business users, what are the end users really doing with this software? And they take that monitoring, they go back to the planning process. Well, we built this feature, and it's being used this way. Wouldn't it be interesting if we did the following? And that trade-off. So because they're getting on the same page with the business use, they become much more part of the product-driven organization. And you'll notice that in here, in that description, in that product-driven description, there's no program managers or project managers, there's no QA department, there's no ops department, there's no security department, because the developers and the product planners have end-to-end responsibility for this. And that's where you want to get to. And you can get there by taking one short step into containers that will greatly increase the reliability and efficiency of your environment. So, any questions? Yes. I'm sorry, can you repeat that? This model? Yeah. So the question is, how does this actually work in a production environment? So the Docker containers or developers or... Okay. Okay. Yes. So here was the question. Let me repeat the question. I think that's very good. What are you doing if you're in an environment, very large organization, they've invested a lot of money in, say, Oracle WebSphere to run their web applications. They have shared hosting, and your application is built in a very large deployment file that sits on those shared web servers. And we're going to come in and say, no, we're going to run ours in Docker, and we're not going to use that shared infrastructure. So that exact model was the genesis of this presentation. That's what we did for a very large telecommunications company that was running some core financial systems in their environment. The financial systems that they're running is tied into sales that goes on in their retail store. The information comes into their back office and is processed by this system to produce financial results and make other decisions that go back out to the retail store. So it's important that this thing be running. Anytime the retail stores are opening, this thing has got to be responding to requests in real time. So it was 24 gigabytes in size. It was written as a Java WAR file that ran on a very large WebSphere environment. And what we did was to take that system without changing the application code. We built a Docker container that started with Linux, put the WebSphere image on it, then installed the WAR file into it. So now we had an image with Linux, WebSphere, and our application, and that ran standalone. And we built that Docker image, and as I said, it is 15 gigabytes in storage and 20 gigabytes at runtime. And then we put that on their Kubernetes cluster. So in their Kubernetes cluster that was expecting to get microservices in the 2 to 3 megabyte range, we put a 24 gigabyte legacy application on that cluster. We learned how to manage that. It did not take but a week to figure out how to manage that in test, and that learning was applied to prod. So it took a little bit of tweaking in terms of how they set up the rule set in Kubernetes to do that deployment to make sure it worked right. But end to end, it took less than a month to be able to take this application, put it into a Docker container, and put it onto that next level of a Kubernetes cluster. If we'd gone straight to Docker, we wouldn't have had to care about what Kubernetes was doing with it. We put it on Docker and run it essentially on the same hardware that it was running before. So in this case, we were able to deprecate some WebSphere hosting systems and merge those, reuse that compute hardware elsewhere in our organization. So if we'd done that with Docker, we might have put Docker directly on those hosts, which was a plan at one time, was to put Docker directly on those hosts. Instead, we went to Kubernetes. But that was exactly that legacy scenario where we said we were going to Dockerize this thing. And since then, as proof of pointing, we've been able to get features out 2 times faster than we were before, because the Docker container allows us to test it. It starts faster. Developers can start it on their own rather than waiting for a test organization to start one up. So they get much quicker feedback on the features that they're building. When they do run those and test those features, they can get the business to review the results quicker. So it's all in all, it's doubled the speed at which they can develop and add features to this, which has doubled the features that they're able to advertise in the retail store, which has increased sales. So in a very large enterprise that was very slow to move, we did exactly this, and we're able to get a huge benefit out of it.